Great, and thank you for the introduction. I guess that means I can slip the introduction to myself. So just going on from that, today I'm going to be talking about the fabrication of chemical microswimmers or photochemical microswimmers. I think given the audience that we have here today, it's not really so necessary to go into specifics, but as a general overview or recap, of course, at these length scales, you have low Reynolds number regime, which means that the particles low Reynolds number essentially means that the viscous forces will dominate over the inertial, which means that for the particles to move that we're studying, you require the breaking of the time reversal symmetry property. So this is achieved in various ways. One of the most common ways that it's done is to produce Janus particles. So these are particles with a geometric asymmetry in their surface properties. And in particular, one popular method that is used is to produce so-called chemical microswimmers, which essentially have this Janus structure where the asymmetry is in the catalytic properties of a particle itself. So as you can, basically what happens is that because you have an asymmetry in the catalytic properties, you have an asymmetry in the product species which are produced, which then results in a pressure-driven sort of flow around the particle surface, which then induces a motion of the particle itself. And within the field of sort of chemical microswimmers, you then have a further subset of photochemical microswimmers where the catalytic properties are given by a photocatalyst, which allows you to have light-driven motion and provides you control. And here on the right, we have an example of a system that I was studying, basically where the particles are moving. And then on the left, this is the Janus sort of structure I mentioned before, where you have half of a particle decorated with these photocatalytic nanoparticles. And I'll come to this in a moment. So one of the main challenges right now facing the application of Janus colloids active matter as a whole to real-world systems is that the fabrication is quite difficult. So there's sort of two main challenges, as I see it, and I think as the literature sees it, when it comes to the synthesis of such structures. So even though Janus particles seem to be very simple on the face of it, in reality, achieving this asymmetry is actually quite difficult. So one popular way that this is done is, or the most common way, which I'm sure many of you are familiar with, is essentially sputter coat monolayers of particles. Now, I think it doesn't require much explanation why sputter coats are basically using a high vacuum environment where you're sputter coating a very expensive metal precursor in most cases is not something that you can really consider scaling to larger quantities of particles. In addition to this problem, actually producing the monolayers themselves is somewhat tricky because you have this issue of multi-layer stacking where you have multiple layers of particles stacked on each other. So to sort of circumvent this, what is typically done is that dilute suspensions of particles are spread on the, say, a glass slide. The problem with using dilute suspensions, of course, is that, again, from, say, a single glass slide, you might have a yield on the order of micrograms. So this is really very, very small quantity of particles, which really limits your ability to actually use them for any engineering applications. To sort of circumvent this problem, one thing that was a technique that was developed in the late 2000s was this so-called Pickering wax emulsion technique to produce Janus particles as a whole. So this is a very nice technique, and basically a Pickering emulsion, as described in this graphic here, is essentially an oil and water emulsion where the oil droplets are stabilized by the absorption of particles at the interface of the oil droplet itself. And the Pickering wax emulsion technique, the oil used is actually molten wax. And the reason for this is that upon cooling, the wax will solidify, basically allowing you to freeze the particles in place. And what's good about this is it means that you can actually modify the outer surface of the particles and the wax will act as a mask, preventing the inner side. So if you can see here, the inner side of the particles within the wax will be unmodified, where the outer side will be modified. And then upon dissolution of the wax, you're able to get these Janus structures. And here's an example that I have of the so-called colloidal, which is basically the oil droplet. So the wax, solidified wax in water with the particles around it. The problem with this technique, so this really addresses the scalability factor, but there's still the issue of a lack of material options. Like what do you actually functionalize the particles with? Like what kind of films can you achieve? And so what we propose to do for the synthesis of microswimmers is to use pre-synthesized nanoparticles to decorate the colloidosomes that I showed previously, and thereby obtain microswimmers which are asymmetrically functionalized with nanoparticle thin films. So in order to do so, and doing this, we are able to really extract information from this really large field known as colloidal nanochemistry, which, as the name suggests, is basically focused on the synthesis of nanoparticles. Now, the reason for the interest in nanoparticles is that as you go to the sort of a nano regime in terms of materials like metals and metal oxides, you get these very interesting properties emerging due to confinement effects, amongst others, which are very promising for applications, and in particular for catalysis. So you can imagine that for a chemical or photochemical microswimmer system, which depends on catalysis or photocatalysis, of course, the better the catalyst you have, the better it is for the swimming mechanism. And in addition to this, like really in the literature, there are thousands, if not more, of strategies which outline how you can obtain or synthesize nanoparticles with different compositions, so mixtures, alloys, different shapes, different sizes, all with, of course, their own unique properties. So you can start to envision a methodology where you have a desired application in mind, and then you select a nanoparticle with a functionality that you want to encode to your microswimmers and really have designer microswimmers suited to your application. So just as an example, like with regards to the photochemical system that I'm looking at, you can consider, say, the titania, so titania photocatalyst. So already going to a nano-size titania is advantageous because you have the advantages of high crystallinity and high specific surface area, which come with using nanoparticles. But in addition to this, you can consider increasing the efficiency of a photocatalyst by introducing co-catalyst metal nanoparticles, which might increase the efficiency, say, through for example, reducing the rate of charge recombination or introducing heterojunctions, or even extending the wavelength of absorption of a photocatalyst, so for titania from UV to visible light by introducing plasmonic nanomaterials that might be able to inject hot electrons into the photocatalyst itself. So the idea here is essentially really use this vast library of pre-synthesized functional nanoparticles that exist in the literature and obtain microswimmers which are functionalized asymmetrically by these photocatalysts or catalysts. So this then brings me to the actual work that we did. So this is a schematic. So here again, we use this well-established Pickering wax emulsion technique, and we improve on it essentially by using a modular multifunctional polymer bridge, which I'll describe in more detail, and then attach the nanoparticles via the bridge, and then remove a wax to obtain our photo-responsive Janus chemical microswimmers. So with regards to the polymer itself, we use a polymer that is based on this pentafluorophenyl acrylate submonomer unit. And what's nice about this is it has this really good leaving group of a pentafluorophenyl. So you can use you first synthesize the polymer, and then you can functionalize it, post-modify the polymer itself, and introduce various functional groups. And the requirement is that the functional groups have a separate sort of a nucleophilic additional group, which is able to knock out this pentafluorophenyl group and then post-modify the backbone. So in this case, what we use is this amine functional group. So this is sort of a link. This is basically what will donate the electrons to kick out this pentafluorophenyl group and then bind and form this amide sort of structure here, and then introduce the functional groups that we want onto the polymer, and thus allow us to modify the sort of microparticle support with what we want to do. So in the case of the work I'm describing today, the functional groups that we used were one, nitrocatechol. So this is a nitrodopamine group, and we introduced the nitrocatechol functionality because it allows you to, it binds to covalently to many metal oxide surfaces through a chelation chemistry mechanism, which is a very strong chemical bond. Two, we introduced the silane groups for this aminopropylsilane, which forms siloxane bonds with the silica microparticle support. Again, very strong, it's difficult to break. And then finally, we introduce a diamine, which we then protonate. And the idea here is that you have this electrostatic positive charge, so that will allow the polymer to come close to a negatively charged silica surface. It also screens the charge between the negative silica surface and the negative titania surface. And as well, it enhances dispersibility and prevents and allows the polymer conformation to sort of lie across the silica surface rather than collapsing in on itself. And so with all those sort of schematics and details out of the way, this is actually the experimental realization of work I've described. So here you have the colloidosomes. You then functionalize it with a polymer and the titanium nanoparticles. And then you remove the wax to obtain these Janus morphologies, where you have this asymmetry in the photocatalytic nanoparticles, which we also visualize with EDX spectroscopy on TEM. So one thing that's quite interesting here, which was actually a bit fortuitous, was that the penetration of the particles, as you can quite clearly see, is not 50%, but the modification is 50%. And this sort of hemispherical coverage of nanoparticles, or in general of the catalytic film, is advantageous because towards the wax surface because of the densely packed monolayers, which you can see here. So the nanoparticles essentially can't reach the wax space because of the particles which are in the way. So this is was quite a nice accidental finding. So now that we have our chemical microswimmers, okay, well, do they move? And yes, so we put them in hydrogen peroxide, we illuminate with UV, and as expected, they do swim. What was interesting though is that they actually showed this 3D motility. And the reason why this is interesting is that typically in the literature, and in fact in experimental realizations of chemical microswimmers, the motion is typically limited to 2 dimensions. So just starting with the sort of the simulations or theoretical aspects of the motion, the most popular, I think would be fair to say, model to describe the motion of Janus microswimmers is the active Brownian particle model. And here you have a constant propulsion force, you have Langevin dynamics, and you have a orientation vector, which in the case of a 2D orientation particle, so it swims in XY in 2 dimensions, it has a unit vector sort of which freely diffuses across a unit circle. So the orientation is always in 2D. You then also have a 2D swimming with a 3D orientation vector where the unit vector sort of orientation is diffusing on a unit sphere, but then you look at the projection onto the XY plane and the particle still swims in XY. Of course, there are people that have studied this sort of true 3D motion of swimmers. However, the point is that a lot of studies have demonstrated that, in fact, this 2D sliding state, as it has been called, is the favorable state for the motion of particles. So a particle might start out of plane, but it will come towards the surface and slide along it for a range of experimental conditions. And the reason for this is attributed to basically a hydrodynamic coupling of the flow fields generated by chemical platinum silica microswimmers, at least they swim in plane and they stay in plane. But again, coming back to the system developed here, what we see is more of a 3D motion, but it's not true 3D motion, it's more 2D motion with short ballistic segments out of plane. So here we have an example trajectory where the particle ballistically moves out of plane, comes back down. But more quantitatively, we can see, for example, here that, so this is across multiple particles, so the orientation vector. So here we have the orientation that the particle makes with respect to the substrate. So plus 90 means it's swimming directly out of plane, and minus 90 means swimming directly to the plane, essentially. And we see that although, of course, most of the time the particles are swimming in plane, you also observe these sort of exponential tails where the particle does swim out of plane. And then looking in more detail, we see that the actual orientation that the particle makes when it's moving with respect to the substrate affects its speeds. So to look at this in more detail, I've got this slide here. So I did some experiments where I showed that the particle, at least in experimental conditions used, will swim cap first. So the titanium cap swims first. And in fact, what's interesting here is that we see the 2D sliding state, which is commonly theorized. So that gives us an indication that it is present in our system, but there's an additional component which is making them swim out of plane. And so bearing in mind that in our systems, the UV light source is coming from the bottom, and that the cap swims first, we can try and understand a bit about the distribution of the velocities as a function of the orientation. So at minus 90, so this is where the particle swims towards the substrate, towards where the light source is, with the cap first. We see the faster speeds. And this can make sense when you think about in terms of, okay, the full cap is illuminated. And as well, you have gravitational effects. So that seems quite intuitive. What's maybe a bit less intuitive is why the particle can actually swim out of plane in the first place if it's swimming cap first. So there's quite a bit of literature about this sort of self-shadowing effect of the particle, typically titania systems, where they're able to use the fact that the titania absorbs the light as it passes through, which means that the particles have this sort of photogravitactic motion where they only swim up out of plane because they've got like a dense titania cap and no light can pass through. They don't swim back down. But as I said, what we find is the particles swim up. And in fact, if you look at the transmissibility of silica, of UV through silica, you see that it's quite reasonable that the light is able to pass through the silica particle itself and then, I guess, reach the titanium nanoparticles. So what we expect to occur is that if you can imagine this system here, as described, you have a UV light coming through. The light is able to pass through the silica and then be absorbed by titanium on the other side, creating a sort of a ferritic gradient, causing the particle to swim cap first. And this is why we observe this swimming behavior upwards. However, this still doesn't explain, as I said, why we observe a 3D motion and we're just not the 2D state. And we propose that there are two contributing factors towards this. So the first is we just looked at the passive system. So no UV light, they're just diffusing. And what we see is that the particle is freely diffusing. It's got a free rotation in 3 dimensions. And we expect that because of the lightness of a titanium cap, so we don't have a dense film, we have nanoparticles, sort of agglomerate structures, the particle doesn't have a bottom heaviness to the same extent that other systems might have, which allows it to rotate better in 3D. In addition, you sort of have an asymmetric distribution. So not just a Janus asymmetry, but really the nanoparticles are fractal aggregates. So they're not perfectly uniform like a cap might be. So instead, this asymmetry might also induce an additional angular sort of rotation through the thermal fluctuations. And staying on the concept of this asymmetry of the film itself, I've got an example here of a tumbling particle. So you can see that, so this is obviously an exception. Not all the swimmers look like this. Most of them swim normally in 2D with these ballistic out of plane motions. But occasionally I would observe such particles like this. And this implies that you really have a strong angular velocity component. And what we expect to be occurring is that because we're using nanoparticles, and again, they have this asymmetry, you've got large chunks of titania dotted around, they have a much stronger angular velocity component compared to traditional thin film systems, which are deposited. So the combination of the thermal fluctuations plus this active angular velocity, we think are in competition essentially between that and the sliding state, which means that on occasion, the particle will leave the plane because it's got a much stronger driving force to do so. So just changing the topic slightly, having described the sort of motion, maybe some of you are thinking, well, we have these particles and we bind the nanoparticles to the silica particle through an organic polymer. And of course, we then place them in a very oxidative environment of H2O2 and then illuminate them with UV. So UV plus a photocatalyst plus H2O2, it's really like the classic example of how to degrade an organic species. So the question is, of course, well, are the nanoparticles going to fall off? And this was something that concerned me, but it does seem like the polymer that we use is stable to the conditions used. So that's a positive sign. And then staying on the polymer, we can think about extending basically what I showed here. And remember, I began the introduction by talking about the range of colloidal catalysts that one could think about incorporating into the microswimmers. And today, all I've really been discussing is P25. So of course, I tried some different phases of titania just as a demonstration that works for different phases of titania, fine, but also different metal oxides, so strontium titanate and iron oxide. And in all the cases, the nitric catechol chelation chemistry works nicely. And there's no reason why it wouldn't really extend to the detransition metal oxides, like vanadium oxide, etc. That should really be fine. So it's quite self-contained in that respect. So you can really think about getting different metal oxide nanoparticles and decorating your particle according to the application that you want. What's also nice, though, what adds an additional component of modularity is that the polymer, because it has this ability to be functionalized with different groups, as long as they have this electron donating group, you could think about adding thiol groups. For example, if you want to attach gold nanoparticles for thermophoresis, you can instead of nitric catechol, you can put in a thiol group. The thiol would have to be protected probably initially, but that would be fairly straightforward. And then remove the protection, and then you have a thiol group, which you can then bind very well to a various range of noble metal nanoparticles. So really, this approach gives you the option of attaching different types of nanoparticles. And also on this point, we just, as a comparison to show the importance of catalyst selection and why thinking about these catalytic considerations, which are common in sort of colloidal nanochemistry, are important to think about or bear in mind, is that changing the nanoparticle, even just changing the phase of the photocatalyst that you use, can have a significant influence on its swimming activity. And this is on the basis of photocatalytic activity. So we see, for example, for the P25 system, which is a well-established industrial photocatalyst, which is a mixture of anatase, rutile, and amorphous bases of titania, we see much higher swimming speeds compared to just the amorphous phase itself, which is known to be quite photocatalytically inactive. So again, it gives hints that we can really tune the activity of the microswimmers. And so this leads me finally to the outlook of the future planned work, at least on the synthesis side of what I'm doing and of sort of this work, which is that by adjusting the ratio, say, of titanium and iron oxide in this case, or titanium and any other metal oxide nanoparticle, you can start to make mixed films of mixed composition and impart different functionalities onto the microswimmers themselves. So of course here I tried with different amounts of iron oxide because it's really the simplest thing to test essentially. And we see that as you increase the amount of iron oxide in the system that you add with titania, you increase the amount that's found in the film. And this is to be expected because it all follows the same chemistry. And what's nice is that even at the lowest iron oxide concentrations that we add, we already see this steering effect. So this is the same particles, one with the light off and light on, and we see that instead of following this sort of active Brownian dynamics, they all swim towards the direction of a magnet, which you kind of expect when you put magnets in, but it's a nice demonstration, at least as a first step. And so with this, I'm brought to sort of the conclusion slide. So the Toposelective Nanoparticle Attachment, as described, sort of really provides you with a modular pick and mix approach to scalable microswimmer synthesis. So not only can you choose different types of nanoparticles, but you can choose how you're going to functionalize the polymer to get an optimal combination. And this sort of goes to the idea of obtaining designer microswimmers by selecting different combinations of functional nanoparticles for the application that you might have in mind. And finally, at least for the systems described here today, what we see is that you have an orientation-dependent 3D swimming behavior. So this is not only interesting on a more theoretical level, trying to understand the competition between the two driving forces, but also as well, when one comes to thinking about applications or say their use in a microreactor sort of situation, you could try and exploit this sort of complex interplay between gravity and the direction of the light that you use. So it's quite interesting, I think, as a question as a whole. And with that, I'm essentially finished with the presentation. And of course, for more specific details, I can refer you to the recent publication that was published in Advanced Functional Materials. And finally, I would like to finish by thanking, of course, my direct supervisor, Lucio Isa, who's the head of the Soft Materials and Interfaces group. Fabio, who really came up with the idea of trying to use these functional nanoparticles as the basis of a photocatalytic system. And then Nick Spencer, who suggested the use of this polymer, which he had previously worked with, without which I'd probably still be stuck trying to get the nanoparticles onto the microparticles. And of course, everyone in the group for their various contributions during the first 2 years here. And yes, that is the end, and I'd welcome any questions.
Thank you, Maximilian. Very nice talk. Let's see if there are any questions from the audience. Can you see the question in the chat box?
Right, sorry. Okay, yes, so this is true. So in the initial work that was done, I used basically, there's two parts to it. The first part is getting the images that you need to be able to track the 3D motion. So there's this thing called color illumination, where you're able to see the difference in the diffraction ring patterns of the particles. So if you can imagine taking a Z stack of a particle, its diffraction pattern is going to change based on how far you are below it or how far you are above it. And from there, you can get like basic images, which give you an indication of where roughly the particle is with respect to the 2D plane that you are. So what I did for this work was to look at basically the moments of inertia of the image that I was studying. And then sort of, I had a lookup table, essentially. So I had the values of inertia and what they corresponded to in terms of the Z height. And then I was able to say, okay, for this inertia value, you have approximately this Z height and then fit a cubic spline. I have to say now, after spending a bit more time on the problem, I'm not the happiest with it because it's very, like, if you do everything on the same day, it's okay. But between days, between experiments, it can get a bit, you have to redo everything. So now I'm working, well, I've developed some machine learning algorithms to try and do this better, and try and extract out essentially image properties rather than one. So now try to use multiple properties of an image and correspond that to a specific Z height, if that makes sense.